All right, class, welcome back to the next lecture in the equilibrium series, and we are going to section 13.3 in your OpenStax textbook, and this is going to discuss what is known as Le Chatelier's principle, or in a more general sense, it is how equilibrium will shift and adapt when you start making changes to the system. So that's what we're going to take a look at here. So what can affect equilibrium? There's a couple of things. The concentrations, this is for both your products and your reactants. The pressure, the volume, and those two are going to get coupled together when we're talking about gases. Pressure, we know PV equals nRT. So pressure and volume share that inverse relationship. And then temperature can also affect this. Now, out of the bundle here, and we'll summarize this in a few minutes, temperature is the only one that has the ability to actually change the value of the equilibrium constant. So when you change the temperature at which the system is operating, you don't only disturb the equilibrium and create shifts in the equilibrium process, but when it reestablishes equilibrium, it will set up a new Kc or Kp value because you're actually tinkering with thermodynamic parameters, which is going to change the overall position of the equilibrium in terms of the reaction itself. The other three, concentration, pressure, and volume, that can make shifts temporarily in the equilibrium, but it will shift around in order to reestablish the same Kc or Kp, provided the temperature is constant. So what is Le Chatelier's principle? In one statement, it's if external stress or change is applied to a system that is currently in equilibrium, the system's going to adapt and adjust accordingly in order to reestablish that state of equilibrium. So systems that are in equilibrium like to stay there, and if they are tampered with, they will reestablish equilibrium by making the changes necessary if possible. So we're going to see Le Chatelier's principle put into action over the next couple sets of examples here, and then we'll bring up the whiteboard to actually look at it with a real problem. So let's start with changes in concentration. When you change the chemical concentration in a reaction, the reaction is going to proceed in the direction according to the change. So it depends on whether you're going to have an addition or a removal of material. So you can see several examples that I've highlighted here. If the reactants are going to be added, so if you're providing additional reactants to the left side of the equilibrium equation, then the equilibrium will shift towards the products. And that's because if the equilibrium was already established, if I pile in more reactants, it didn't need those reactants or the additional amount of reactants in order to be in equilibrium. And so that disrupts it, and the system starts to retreat over to the products in order to use up some of those reactants until the concentrations come back into equilibrium and provide that same Kc value that is established for the equilibrium at a given temperature. Remember, temperature has to be held constant for that Kc value to remain constant. All right, if the reactants are removed, the opposite. The equilibrium will shift towards the reactants because now I'm taking away some amount of material, and the equilibrium wants that material back if I'm decreasing that concentration in order to reestablish the Kc value. Okay? If products are added, equilibrium will shift towards the reactants. If products are removed, the equilibrium will shift towards the products because you are, again, removing something. It wants to replenish it. Okay? Removal will lead to the replacement of what was removed, and addition will lead to a drive away from the excess additional material added to the reaction. So that's how manipulation in concentrations will affect this. So in many of the Le Chatelier principle questions that you come across in textbooks and tests and quizzes, it will give you a reaction, set it up, and then it will say, what happens if you add reactant B? What happens if you remove product D? What happens if you change the temperature? And so on and so forth. And you have to basically play the role of governing, will the reaction shift left or will it shift right? Will it favor the products or the reactants as it starts moving back and forth in those changes? Okay, now let's talk about a change in pressure and volume. Pressure and volume are inversely related, so that means as one goes up, the other goes down, and vice versa. As pressure increases, volume is going to decrease. And as volume decreases, the concentrations will go up accordingly. So keep in mind concentration is going to be moles over liters if we're discussing molarity, which is the general unit we use. So as the volume decreases or shrinks, that means your concentration is going to increase because it's in the denominator. So keep in mind that this is going to apply to gases. PV equals nRT is a gas law. It is not that you can't change the pressure or volume for a liquid or a solid system, but in general, solids and liquids are not going to react to pressure changes as well as gases will. And so we tend not to consider these pressure changes when we're discussing aqueous phased material. It's usually reserved for gases. Right? This leads to a situation where the change in pressure and volume may shift the equilibrium, but it will not always shift it. And you have to pay attention. So the key is going to be in the concentration increase of products relative to reactants. So keep in mind, we have stoichiometric ratios in these balanced equations. And when we have these stoichiometric ratios, those values are pulled out of the balanced equation and they are used as exponents for the products and reactants that they are found next to. So that means if I'm going to change the concentrations by changing the pressure or the volume, that I may change those concentrations exponentially compared to others. It depends on if everything is equal on both sides as far as stoichiometric moles. All right, so you can see the last note here. If stoichiometric moles are equal between reactants and products, meaning the delta N is 0, we have the same amount on each side, this will lead to no position change. The equilibrium will just stay right where it is, content, whether you are increasing or decreasing the pressure. However, if one side of the reaction has an outnumbering of stoichiometric moles, the concentration growth will be disproportionate for that exponential factor in comparison to the other materials. And that will make the reaction shift towards the side with weaker concentration. So take it back to concentrations. If I have one reactant that only has a stoichiometric ratio of 1, and then the ratio for the product is 2, that means the product in that numerator is squared. And so its growth is going to be squared in concentration as we manipulate this. And because of that, it means that we'll have more rapid growth of that numerator, and therefore the equilibrium will shift towards the reactants, the denominator, in a case like that. So again, if the words aren't making sense, I totally understand. We're going to actually outline an equation at the end of the lecture here so that we can walk through this. And obviously, we will be practicing this in class. Okay, changes in temperature. So you need to, when you start looking at a change in temperature, consider or go back to thermodynamics, particularly enthalpy, delta H. So delta H is used when we start talking about heat, and we talk about endothermic and exothermic reactions. So what you need to do here is start thinking about heat as a product or a reactant. So heat can be generated or it can be consumed. If it's generated, we're talking about exothermic reactions, and if it's consumed or required, that would be an endothermic reaction. Okay, so if you have an endothermic reaction that's consuming heat, okay, the heat can be viewed as a reactant. It's something that needs to be consumed, right, in order for the reaction to proceed forward. So let's correlate this to temperature. A rise in the temperature is going to be viewed as adding heat to a system. Now, temperature and heat are not the same thing, right? Temperature is almost more a measurement of heat through the measurement of energy in the system, right? But while we're measuring that, if the temperature increases, how do we increase the temperature? We provide more thermal energy, right? More heat into the system. So a rise in temperature can be viewed as adding heat to a system, while a decrease in temperature can be seen as a removal of this heat. So the systems are going to fluctuate accordingly. What you need to consider here is the enthalpy value. Do I have an endothermic reaction or an exothermic reaction? And this is so important because you are going to, when you look at the temperature change, you have to match it to whether you have endothermic or exothermic. In other words, will heat be considered a reactant or a product as a byprocess of this reaction? So let's pull up the whiteboard, actually run through an example and give some examples, and then we'll come back to wrap up the rest of this lecture here. All right, so let's use a practice problem to discuss shifts in equilibrium. So I'm going to use a relatively simple example, and we will go through some additional ones in our classwork. But I'm going to take N2O4 in a gas state, and we'll set up the equilibrium with nitrogen dioxide. And I am balancing this right here. So the first thing I want you to consider that we talked about are the concentrations. So what's going to happen if I add N2O4 to the system that is in equilibrium? And I'm going to put a couple of these here, so be thinking of them as I write them and the direction we would expect the shift to occur. So what would happen if I'm going to remove N2O4? What would happen if I add some of the products, some nitrogen dioxide? And what would happen if I remove some of the nitrogen dioxide? Right, so if we take a look at this, and I would always encourage you to pause the video and try to work through these before you unpause it and go through the walkthrough. Okay, adding N2O4 is going to proceed towards the products, and that's because I'm adding additional reactant that was not needed. So therefore the equilibrium will shift over to the right. Now the removal of the N2O4 will have the opposite effect. I'm taking away some of the needed N2O4 concentration. The system has to produce some more of that in order to reestablish the Kc in the proper ratios. All right, now if I add the N2, I'm adding products, so we shift towards reactants. We don't need that additional product. And if I remove some of my product, again, I'm going to shift this way over towards the product because I need to replace some of it. All right, now I want you to consider what would happen in a situation where the pressure is going to increase and the volume is going to decrease. All right, so what I'm going to need in order to consider this is I want to take a brief look at Kc here. So Kc is going to be the concentration of nitrogen dioxide squared due to the stoichiometric coefficient over the concentration of the dinitrogen tetraoxide. Now keep in mind that in a situation like this, I have the squared growth up here, whereas at the bottom I do not have that squared growth. So as the volume decreases, both of these concentrations are going to increase simultaneously. They're both going to be increasing. But the real question is, are they going to be increasing at the same rate or at the same pace with one another? And the answer here is no. I've got the squared growth up top, whereas at the bottom here, I only have the regular growth. And so because of that, what you want to consider is the concentration of the nitrogen dioxide will be increasing at a more rapid pace. And therefore, I'm going to expect a shift away from that over to the N2O4. Right? So you have to evaluate the Kc. You have to actually take a look at that and think whether that is something where you have the growth being steady between the two of them, or you have one that's going to be growing at a more rapid rate. So what I can tell you is, in a situation, let's say that this squared value was not here, and it was just a 1-to-1 ratio. In that case, there's no shift in the equilibrium. So we will come across equations where that change, right, or what we would call the delta N, the stoichiometric ratio of products and reactants in terms of total moles, are equal to one another. Well, in that case, we're not going to have any type of equilibrium shift. All right, now let's consider the last of the factors, which is temperature. So what's going to happen if we increase temperature, and what's going to happen if we decrease temperature? So you might think for a second, hold on, I can't answer that, and that's correct, because what I would need to provide here, and what will be provided in these types of cases, is the delta H. So you need to know the enthalpy of the reaction. You would have had to either calculate it yourself and figure it out, or it has to be provided to you. So in this case, the delta H for this reaction at standard temperature is going to be 58.0 kilojoules per mole. So that's a positive 58.0. So what that means is that we can rank this as endothermic. Now I want you to think for a second what that is going to mean in turn. If this is endothermic, it means it consumes heat. So rewrite the reaction with heat being consumed. That means heat is a reactant. So I can rewrite this as heat plus N2O4 gas is in equilibrium with 2NO2 gas. So now this can help students sometimes visualize this to an easier extent. Here's my heat. So if I increase my temperature, what do I expect to happen? Well, an increase of temperature, we can view that as an increase of heat being put into the system. So I'm adding a reactant. So in a case where the temperature increases, I expect a shift towards the products in this case. And that's because I'm adding additional reactant. I'm adding additional heat. It's not technically a reactant, but you can view it as a consumable thermodynamic value here. As I'm talking about the heat and I'm pumping it over into the reaction. So I would expect the opposite. If I lower the temperature, that means the heat, the system's going to be losing heat. So some of this is going to be drained out of the system, right? And in a case like that, I'm going to shift towards wherever the heat was, which means I will drive the reverse reaction here. Hey, now keep in mind, this is an endothermic process. So if we had an exothermic process, we would see the opposite trends that are going on here, because then heat is a resulting product. So an increase in temperature means I'm adding product, and therefore, if I'm adding product, I retreat back to the reactant side. Right? So hopefully this example has helped to show you the shifts or the changes we can expect when we're dealing with Le Chatelier's principle and the various parameters we can manipulate. Okay, so to wrap this up briefly, let's talk about Kc and variables, because that's what we just went through. It is important to remember that only temperature can change the actual equilibrium constant value, as thermodynamic parameters are being driven, enthalpy in particular, to re-equilibrate. Right? So concentration, pressure, and volume will all shift the equilibrium process back and forth, but the constant, meaning the Kc value, will not change after this is reestablished. It will simply move around until the ratios are correct and that Kc value can be reestablished. All right, so that is going to conclude Le Chatelier's principle and the lecture regarding the different factors that can affect equilibrium. And up next will be the final lecture in the basic equilibrium course, which is related to section 13.4, and that is going to be equilibrium calculations. So I will see everyone over in the next lecture, and thanks for your attention during this learning process.